Imagine you are trying to teach a machine learning model about something complicated, like house prices or income levels. Often, the numbers you collect are not neatly distributed, with many values clumped at one end and a long tail stretching out to the other. This unevenness can sometimes trip up your model, making it less accurate. The direct answer is no. Not all skewed data needs a logarithmic transformation. While it is a very powerful and commonly used tool, its application depends heavily on the nature of your data, the specific machine learning model you intend to use, and the problem you are trying to solve. Data skewness occurs when the distribution of a variable is asymmetrical, meaning it has a long tail on one side, typically the right side for positive skew. Many statistical models, especially parametric ones like linear regression, assume that the input data or their residuals are normally distributed. When data is highly skewed, it violates these assumptions, which can lead to biased parameter estimates, incorrect standard errors, and ultimately a poorly performing model. A logarithmic transformation helps by compressing larger values and expanding smaller ones, effectively reducing the skewness and making the distribution more symmetrical, often closer to a normal distribution. So, when should you consider this transformation? It is most beneficial when dealing with data that exhibits a strong positive skew, such as income, age, or population figures. It can also be crucial if your target variable in a regression problem is skewed, as models often perform better when predicting a normally distributed outcome. Furthermore, transformations can help stabilize variance, which is another common assumption for certain models, and reduce the impact of outliers, which tend to reside in the long tail of a skewed distribution. You would evaluate the need for transformation by looking at histograms and QQ plots of your data, and by observing the performance and residual plots of your initial models. However, it is important to remember that logarithmic transformation is not the only option. Other nonlinear transformations like square root, cube root, or more adaptive methods such as the box-cox transformation or Yeo-Johnson transformation can also be effective. The box-cox transformation is particularly versatile as it can handle various degrees of skewness and aims to find the optimal power transformation to achieve normality. The Yeo-Johnson transformation extends this capability further by being able to handle data that includes zero or negative values, unlike the standard logarithmic transformation. Choosing the right transformation requires careful consideration and often a bit of experimentation to see which method best aligns the data with your model's underlying assumptions for improved performance and interpretability. Ultimately, the decision to transform skewed data is a strategic one, driven by the goal of optimizing your model's performance and ensuring its statistical validity. It is about understanding your data's characteristics and matching them with the expectations of your chosen algorithms, leading to more robust and accurate predictions without blindly applying a universal fix.